everyone, welcome to the second part of our lesson on vector fields. We're going to look here at an example with tips for matching vector fields with plots, and then also do a quick definition of something called a gradient field. So as a quick reminder, a vector field is just a function whose domain is a set of points in either R2 or R3 and whose range is a set of 2 or 3 dimensional vectors. So when we talk about vector fields, the picture to have in mind is a picture of just a bunch of vectors, just a bunch of arrows. And conceptually, we can think of these as representing wind patterns in an area, or ocean currents, or some other type of gravitational force that's at play here. Okay, so in this example, let's look at some strategies for matching vector fields with plots. So the first strategy is to look for plots where the vectors are identical along horizontal or vertical lines. So for example, in plot 4, we see that the vectors are identical along horizontal lines. And this tells us that the vector field here is independent of x. That is, x is changing, that's having no effect on our vectors. And so when we look at our equations, we want to look for an equation that contains no x's. And so hence plot 4 here is going to correspond to the vector field in B, which takes the point xy to the vector 1 sine of y. Okay, now similarly, if we look at plot 1, we see that the vectors are identical along vertical lines. And this tells us that the vector field is independent of y. As y is changing, it's not having any effect whatsoever on our vectors. So when we look at our equations for our vector fields, we're looking for one that does not contain a y. And so plot 1 is going to correspond to vector field C, which takes the point xy to the vector x minus 2, x plus 1. Okay, so that's one strategy, looking for plots where the vectors are identical along horizontal or vertical lines. Now, that's not going to help us in 2 and 3. We need a different strategy. So another strategy is to find the basic direction of vectors in each of the 4 quadrants and see if that can help us match things up. So for example, let's look at the vector field A that takes the point xy to the vector yx. So for example, this vector field is going to send the point 2, 2 to the vector 2, 2. And so we'll do a rough sketch of that. We'll think of a vector in that first quadrant as pointing roughly then to the right and up. All right, what about a vector in the second quadrant? So the point negative 2, 2 will get mapped to the vector 2, negative 2. And so we're going to sketch a vector in the second quadrant that points to the right and down. All right, for our third quadrant, how about the point negative 2, negative 2, which will map to the vector negative 2, negative 2. So we'll sketch a vector that points to the left and down. And then finally, a vector for the fourth quadrant, we'll take the point 2, negative 2, which will map to the vector negative 2, 2. So we'll sketch a vector that points to the left but up. Okay, and so looking at our plots that we have remaining, this seems to match up really nicely with plot 2. And so it looks like vector field A, which takes the point xy to the vector yx, is depicted in plot 2. Now, that means that vector field D, which takes a point xy to the vector y1 over x, should match with plot 3. And this makes sense because our vectors in our plot are decreasing as x is increasing. And so that makes sense for that 1 over x piece of our vector field. Great. Okay, so those are just some strategies, some things to think about when you're trying to match the equation of a vector field with a plot of a vector field. Let's switch gears. The last piece of the puzzle is to talk about something called gradient fields. So if f is a scalar function of two variables, recall that its gradient, grade of f or grad of f, is defined by taking the point xy to a vector whose first component is the partial derivative of f with respect to x and whose second component is the partial derivative of f with respect to y. And therefore the gradient of f is really a vector field because it takes a point xy to a vector. It's just a very specific vector whose components are the partial derivatives. And so we call this the gradient vector field. And likewise on R3, if f is a scalar function of three variables, its gradient is a vector field on R3. It's going to take the point xyz to the vector whose components are the partial derivatives with respect to x, y, and z. So let's do an example. Let's find the gradient vector field for the function x squared minus y. Okay, so we start by finding the gradient. So our gradient of f is the vector whose components are the partial derivatives. And so our partial derivative with respect to x will be 2x. And our partial derivative with respect to y will be negative 1. So we have the gradient vector field, which takes the point xy to the vector 2x negative 1. Let's plot just a few points to get the picture. So this particular gradient f will take the point 0, 0 to the vector 0, negative 1. So we sketch that by starting at the point 0, 0 and sketching a vector which has no left or right component but points just straight down 1 unit. This gradient vector field is going to take the point 1, 0 to the vector 2, negative 1. So starting at the point 1, 0, we would sketch a vector which points to the right 2 units and down 1. And one final one, we're going to take the point negative 1, 0 to the vector negative 2, negative 1. And so starting at the point negative 1, 0, we will sketch a vector which points to the left 2 and down 1 unit. So here are just a few vectors. If we wanted to get a more complete picture of this vector field, we would sketch more vectors or even use some sort of computer program to help us get a better picture of what's happening. Okay, great. So that's all on vector fields. Let me know if you have any questions, and I'll see you soon. Thanks, guys. Bye.